Right. Well, good morning. My name is Jen Bayer. If you don't know me, I work for USGS and PNAP, and I am delighted today to be here with some great speakers and a whole bunch of friends and colleagues to share what is the fifth and final session of the PNAP Fish Monitoring Work Group PTAG Data and Analysis 2025 webinar series, which could be our new longest title. So we love that. I'm very grateful to our speakers today and all through the course of the series. I'm going to ask folks to mute your phone. Pause for a second. I'm getting some background noise. Thanks. Thank you all for coming. Thank you for coming for the previous 4 sessions. It's been a really wonderful arrangement of talks, starting with here's the PTAGIS data system and going on to more complex applications and uses. And today we have more about using R for PTAG data with colleagues Jennifer Fredrickson and Jennifer Rowe from USGS. And then we have some introductions to other regional PTAG systems. Sorry, Amy's looking at me. I think I have another slide. I forgot our welcoming slide. I'm already into the talks today. I'm really excited about this, but I want to pause here on our welcome slide because it is really important to PNAP that everyone know they are welcome. And I'm grateful you're here and I'm grateful to be here. All right, so this is the slide I thought we were all looking at as I tried to briefly introduce our speakers who have their cameras on for now so we can see them all. We're going to go through, we have one sort of longer talk with Jenny Fredrickson and Jen Rowe from USGS, sharing some really cool hands-on stuff using R. And then we have 3 shorter talks where we're going to be introduced to some folks working outside the Columbia Basin, so you can make some new friends and learn about other uses and other systems where you might be able to find information. So I think with that, I'm stalling just a minute. I see people still coming in. This will take, the first talk is about 45 minutes. We'll do Q&A at the end. Then we have 3 talks that are much shorter. We'll have, let's say, like 10 or 15 minutes and have a brief Q&A at the end of that. Each one at the end of all 5 presentations, we should still have time for our office hours, as we're calling it, which is really an extended opportunity for discussion. And so we hope that everyone sticks around for the full 2 hours. This is our last session of the 5-week series. So, you know, any questions are welcome, especially thoughts about what we might do next. And you know that we're going to offer you a survey also. We'll drop that link today and then we'll share it with a follow-up email next week that asks you for your input about what we might do next. And so stay tuned for that. I think, are we ready to go, Amy? Seeing the nod. All right. So with that, our first speakers are Jen and Jenny from USGS, colleagues of mine at the Forest and Rangeland Ecosystem Science Center. And thank you very much for presenting today. I'm going to turn off my camera. I encourage everyone to turn off your cameras unless you're a speaker, just to allow us to focus on them. Thank you so much. We'll have Q&A at the end.
Okay, thanks, Jen, and thanks everyone else for joining today. My name is Jenny Fredrickson, and I am here with my colleague Jen Rowe. We're going to be tag teaming this presentation today, and we work in the Herpetological Research Lab led by Dr. Mike Adams at USGS Fresk in Corvallis. And I did want to do a quick disclaimer here that Jen and I have a lot of experience and expertise in R and data management, but as you can see from these photos that I put up, we are herpetologists, we are not fish biologists. And so we have tried, and Jen especially has done a great job of integrating PTAGIS data for the examples that we're using in this presentation in R. But if something doesn't quite look right, like from a biological standpoint in fisheries biology, there's a reason why we don't work with this extensively. So, you know, please be kind. Okay, so I'm going to turn off my camera here and then get started talking about pulling in data. So first, which is hopefully a review for most of you. So first we'll talk about text files. So it is common for very large data sets to be provided as a text file. And we can use the read table function in base R to pull in text files by specifying the text file here shown in the red text within the quotation marks by specifying the file on your computer. Something really important to remember about text files is that they are not always delimited in a standard format. I personally use pipe delimiters a lot when working with text files, so remember to use the sep argument so that your data is read in and all of your columns show up correctly when it comes into R. This sep argument here is showing how to set the delimiter as a tab delimited. And then also remember to always specify whether you have headings in your data so that it is read in correctly. CSV files, the syntax to reading in CSV files are very similar. Here we're also showing the option of specifying the classes of data in your columns. So you can basically tell R for all of your columns what type of data are in each column. And something that I wanted to highlight here is we're specifying that we're reading in tag codes. Some of these raw data are from the PTAGIS, from our PTAGIS data that have been shown in earlier seminars. And we're showing here that we want tag information to be read in as a character. And this is important because we don't do the PTAGIS pit tag data with fish, but we do a lot of pit tagging with frogs and other herps. And so we know from experience that pit tag numbers are often really long. Ours are typically 16 digits or longer. And R, just like Excel, has a tendency to truncate and do weird things with really long strings like that. And so it's always good to make sure that you're specifying it as a character and R is not doing something weird in the background that you don't want in the underlying CSV. Okay, so importing data from Excel can be a little more tricky. You can't do it in base R. It typically requires a package. And there are several packages for reading in Excel files, but we are using the package Rio here. And this one's nice because if your file has multiple tabs, the Rio package can handle that by importing all of the tags as a list. So right here we're saying we want to import the list of our Excel file, and we're assigning all of the tabs as a list called data. If you just have an Excel file with one tab, you can simply use a function called import. And then if you use the function names and specify that data list that you just created, it will show you all of the names of the different tabs that you're importing in from Excel. So you can see here this pit tag workshop Excel exercise that we imported in has 4 different tabs in it, and they're called interrogation data Lacosa, or Loxa, interrogation summary hydro, etc. So there's 4 of them, and then we can use this function list to environment to basically tell R that we want to call in all of those tabs separately as data frames into our environment. Okay, so getting a little more interesting, we can look at how to use RODBC packages and connections to import and export data from databases. So our example here is going to be using Microsoft Access databases, but RODBC can be used as a connection for multiple different databases. Something extremely important to note is that when you're using RODBC, the R and whatever database you're using has to be running in the same bit version, which is more kind of like basic computer science, I guess, but most programs run in either 32 or 64 bit. And so you can check which version of Access your computer is running. It used to be really easy because in R you used to be able to just switch your R session between 32 and 64 automatically, but all of the newer R versions only run in 64. So if your database or your Access database is running in 32-bit, you're going to need to change that. If you're doing this from an office, like for us at USGS, I had to get my IT person to come help me with that. It's really easy for them to do. I think that they told me they typically run the 32-bit as a default because it takes up less data or something like that, and most people don't need the 64-bit, but they can easily do it for you. So when your versions between R and your database are matching, you can simply load the RODBC package, and then to create the connection and import data, first, you have to specify a file path to your Access database. So we're just doing that here. So we're using the function file path, and we are calling our file path DB, and we're just pointing it to our Access database on our computer. And then we're creating a channel between R and the Access database using this function ODBC connect access 2007. And we're specifying what the argument we want that file path to be that we just created. And then we're calling that connection channel. So once we have that connection set up, we can pull data from our database into R by using the function SQL fetch. And so we are saying we want to pull in a data frame that we're going to be calling dbdat. We're going to use this channel connection that we just created above with those 2 lines of code. And we're going to import a table from our Access database called interrogation detail. And that just copies the entire table in your Access database into R as a data frame. You can also, if you have a really large data set in Access, maybe you have a huge amount of data in a table, but you don't want to bring it all into R, and you have a really nice SQL query already built in Access, you can actually directly paste the SQL query into R and only query that data that you want from your Access table. So to do that, you can do this function called SQL query. Once again, you have to tell R that you want to use that connection to the database that we called channel. And then you simply use the paste function to paste in your query using SQL coding language. So this example here, I'm saying, hey, what if I want to select, 2 columns from my table in Access called interrogation detail, and I might have some criteria, like say I only want to return rows that have column of a greater value of whatever, value or date or anything you want. And then that's going to return into our R environment as a data frame that we are calling query here. You can also append data from R into an Access database or any other type of database. Some important things to keep in mind is that your data must be formatted exactly the same in your data frame in Access, including the types of data that are in the columns to the table that you're trying to append it to in Access. So keep an eye out especially on columns that have things like dates, times, the heading, names of the columns, those all have to be perfectly in sync, or else you're going to get some errors when you try to append your data from R into Access. To do that, you use the function SQL save. Again, you specify that connection you have to your database. This argument data is just saying what data do you have in R that you want to send to your Access database. So we have this data frame that we've called new dbdat that we're going to be appending into the table interrogation detail into our Access database. You're saying you don't have row names, and you're saying append true. So instead of overwriting the data that's already in your table Access, you're just appending it to the end of the other rows that are already within that table in Access. Just important to note here, I'm getting this code is returning an error because I've already saved it. So you can't append data over each other. If you've already done it once, it'll give you an error because you already have that data in the table. But if I tried to save some new data that I hadn't already run earlier this morning, it would work fine. And then typically good practice, once you're done messing around with your connections with an Access database, is to close your channel and then to remove the channel from your R environment. Okay, I'm going to give it over to Jen, who's going to talk about cleaning and summarizing data.
All right. Thanks, Jenny. This is Jen Rowe now, tapping in. So next we'll move on to some common data cleaning and formatting tasks in R. I'll be showing some examples using the Loxa pit tag interrogation dataset that Jenny was just using from Marika's webinar from April 24th. We'll provide the link to the dataset after this presentation. You won't necessarily need it to go through this demo right now. So after bringing in your data, it's always a really good first step to just get familiar with it. So you want to look at the structure, detect any missing values or outliers, and get some basic summary stats. So these functions listed here are almost always present in the first few lines of my code. Structure, glimpse, and head are all really useful for quickly looking at field names, data types, and the first few rows of your data, while summary will give you a quick view of the ranges of your values, factor levels, and NAs. And then I also really like using DF Summary from the Summary Tools package because it provides some extra stats like your standard deviation and your interquartile range for continuous variables. And it gives really nice breakdowns of the frequency of different factor classes and the percentage of missing values in your data set. And so it's really like a nice one-stop shop for your initial data screening and just getting a sense for the structure of your data. So after you inspect your data, you'll likely need to do some cleaning or reformatting in preparation for any analyses. Data exported from PTAGIS or DART will already be really nice and clean, but you won't always be so lucky. So here's a handy cheat sheet that you can use when cleaning data. I'll go over this really quickly, but you'll have this in the materials at the end, so you can run through these functions on your own. You'll be referencing column names and variables a lot in your code, so it's really good to keep consistent and succinct naming conventions. The janitor package clean names function makes it really easy to quickly clean up messy column names. And then there's also the rename function in the dplyr package, which allows you to set replacement names to anything that you'd like for your columns. You also want to determine how to handle any missing values in your data. And here are some of my go-to functions for that, for handling NAs in data. And then similarly, if you have any issues with duplicated data, you can remove duplicate rows, for example, with this function here. And that exclamation mark means remove. Our data types specify the type of data that's stored in a variable, such as whether it's a number, a logical true or false, a character, date, and then there are many others as well. You can set your specific data types for a variable using as, and then the name of the class that you'd like to set your variable to. The left arrow here is saying that we want to perform the transformation on the right side of the arrow, and then assign that transformation to the left side here. So we're basically overwriting the previous data type of this tag code variable here with a new data type that's specified here as .character. And the same with factors, you would just use as.factor to change something like site name from character to a factor. And it's really important to set your data types because it can really have an impact on how variables are treated in analyses. So for example, if you wanted to use antenna ID as a grouping variable for a plot or a random effect in a model, you'll need to set it as a factor. And to set a date variable, you'll use as.date with the name of the variable here. So we have this mark date MMDD YYYY variable, and we're specifying that date variable is in this format: month, day, year, separated with slashes. You can see down here in this table that this is the format that date is in when we initially pull it into our data set. And we can also, so that's how you would transform a character date into an actual date class. And then if you have a date time variable, such as this obs time value, you'll use this as.posixct function. And again, you just provide the name of the variable, and then you specify the format, which is month, day, year, hour, minute, as you can see below here. And then you have this other argument where you can specify a time zone, TZ. And right here I'm just using UTC as my time zone. And once your variables are actually set in date class, you can further parse and manipulate them using other functions like those within the lubridate package. Here we're just creating a new variable year from this date variable obs time value using the year function. And then if we look at the structure of the data that results from all these different data type transformations, you can see now that we have the site name and antenna ID set as factors, and then we now have our dates showing up correctly as class date or POSIX CT, And note that year defaulted to a numeric, but if we wanted to use it as a grouping variable later on, like we will want to change that to a factor. So on to summarizing and reshaping data. The tidyr and dplyr packages were built with a lot of tools for data wrangling, so I used those a lot. They use this pipe structure to actually feed results to the next function, which can really take some getting used to, but it really helps to break up each step in a flow. So you might learn to like it. Here's an example of a dplyr pipeline for summarizing the residence times for each tag in the study area. We start by piping our data, dat, into a function to group it by tag and year. And then we use summarize to replace all the other columns in that data frame with two new summary columns, which are min dt and max dt, which contain the earliest and then the latest date time value for each of the tag year groupings. And then we pipe those results into mutate, which adds a new column, res time, which is containing the time difference in minutes between those columns. And so this is what it looks like. We now have this column res time, which is the amount of time in minutes that each fish spent in the study area for 2024 or 2025. So that might be something that's useful. And here's another example. During your QA process, you might want to make sure that there are no PIT tag entry errors by checking the data against a known list of tags. So here's maybe a list of all the tags that we know were deployed, and then here's our data that were collected. You can use a join from the data frame of your unique tags to your data to find non-matches and potential data entry errors. So here we have another dplyr pipe that's taking the tag list and performing a right join onto the data. So we're joining by tag code, which is the common field in both data frames. And we're setting keep equal to true to keep the tag columns from both data frames. So now you see you have this output that has two columns here, a tag code X, which was from our kind of master distinct code list, and then we have tag code Y, which was from our data set. And these columns should match if the tag is present in both the data frames. If a tag is present in the data but not present in the tag list, it'll show up as an NA. And so if you subset just by those NAs, you can see the tags that were probably misrecorded. And then if you wanted to go a step further, you can create a function. And this function is saying that if the number of NA rows is greater than 0, we want to return the names of those tags that are potentially incorrect. Otherwise, we'll return all tags are accounted for. And creating functions like this can be really great for building into a data QA workflow. Here's another cheat sheet that I will just briefly go over, and then you can use as a reference. These are just some useful base R functions for other common data wrangling tasks, like creating new variables from if-else conditions or subsetting the data, and also formatting text strings. So these are things that I use really, really often when initially sort of just trying to clean data. All right, now we're going to move on to visualizing data. So I'll be demonstrating how to create a couple basic plots, a density plot and a dual axis plot, and I'll be using R's ggplot2 package. We'll again use that LOXA PIT tag interrogation data set for the density plot, and we'll use adult fish passage data and spill data at the Lower Granite Dam that was queried from DART for the dual axis plot. So in R, you can make plots using Base R or the ggplot2 package. Base R plots are really great for quick and dirty visualizations of relationships, and ggplots are a lot more customizable and are generally preferred for making visually striking publication quality graphs. ggplots have more of a learning curve, but they use a consistent grammar of graphics anatomy, which means you can plot just about anything after getting the basic syntax down. You build a plot using one component at a time, added together with plus signs, like you can see here. The most basic plot can be built just by specifying the name of your data set, your data, equal to, and then you can specify your variables or your mappings, which go inside the aesthetics function, the AES function. And then you can set a geometry type, such as a point, line, or box, or others. And this would be just a very basic plot. You only need those three conditions. But usually we want to add other arguments to then set the coordinate systems and the axis limits, customize colors, or add themes to override the default appearance of the plot. And really every component of a ggplot can be customized. And R being open source means that there are lots of extensions on themes and color palettes that you can use to make really standout graphics. There are even color palettes based on The Simpsons or Wes Anderson movies. So if you're like me, you can find yourself pondering text sizes and colors for way too long. But some considerations when choosing palettes are how many distinct colors you need, as some palettes have more than others available. And then it's always really good practice to use colorblind friendly colors or a mix of color and geometry types to portray your data. Moving into our first example, the density plot. We'll be plotting the distribution of tag detections over time for the LOXA sites in 2024 and 2025. And we start by first just pulling in the data using that read.csv function that Jenny went over earlier. And then the PTAGIS query contained an obs.time.value field with date and time that we want to turn into just a date. And then we want that date to actually have a common year so that we can better see the differences between 2024 and 2025 by overlaying the densities for those years. And here, to do that, I'm nesting three different functions so that I can do this in one line of code. But I'll break it down. We're first formatting the date and time into just a month and a day. We're doing that here. We're taking our obs time value, but we're saying we want the format to just be in month-day. And then we're using this paste zero function, which works really similar to concatenate in Excel. And we're just appending this erroneous common date that I randomly came up with of 2020 to the month and day that we created in this format function. So we're saying, all right, now we want the date to be in format 2020-month-day. And then we're finally just transforming that all into a date using as date, and we're specifying that the format is year-month-day. And this will all make more sense in a moment, but it's really useful to have everything in a common year. And the next thing I'd like to do for plotting purposes is just to shorten site name into a more reader-friendly or user-friendly, like readable format. So I'm shortening site name, which is currently in this format of the site code dash the name of the site, into just a simple site code. And we can use the string split I function right here from the stringer package to split the string at the hyphen into two components and take the first component, which is the site code. So when we do that, then we now have a variable set up called site code, which is a lot shorter and cleaner for the two sites in our data. And now here finally is the ggplot code for this plot that I'm showing you to the right. To start a ggplot object, you just need to use the ggplot function and then include the name of your data set, this dat argument. And then we're adding our variables as the x-axis or the y-axis within this AES function. And a density plot only requires one variable, so AES here only includes the x-axis, plus a group and fill argument, which are saying that we want to group and fill the density curves by the grouping factor year. The geometry line here controls the type of plot and can be point, line, bar plot, box plot, density, histogram, and many others. In this case, we're using the density geom, so we have geom density. And this alpha setting within the parentheses is just setting the transparency of the plot. Scale fill determines the colors that we will be using. And if you don't include this, ggplot will just use its default colors. But you can override those defaults with scale manual and then a list of colors, or you can use a palette from a different package like I'm doing here. I'm using a palette from this JColors package. And then next we just have our arguments defining the axis types, the ranges, and the breaks. Scale x date sets the x-axis as a date axis, and here's where having your variables correctly classified as date is really important, because you can use these other functions in the ggplot to modify things like the date breaks and then how you want your dates labeled. So here I'm saying I just want a month, a 3-letter month, and then a day. And note the empty quotes right here. This is just specifying that we don't want an axis label for date. The scale y continuous sets the y-axis as a continuous variable with the title here in the quotes. And then next I'm using facet wrap to take the plot and break it up into panels for each level of the factor variable site code. And here I'm adding a custom theme from the Harbor Themes package that makes the plot area a little more modern. And then these remaining arguments here are just setting the location of the legend, setting font sizes, and then setting rotation of the axis labels. So for this axis text X argument, I'm saying that I want the axis labels rotated by 35 degrees, and then HJust is pulling those labels down to account for that rotation. So there's our first ggplot. And if we wanted to change this to a histogram, it would be really easy. You just have to edit one line of code here. Instead of geometry density, we would just have geom histogram with a couple extra arguments to define the number of bin breaks and then the position of the bins, which can be stacked or identity if you want them side by side like I do here. So looking at these cursory plots of tag detections over time might make you curious about other questions like the time frame with the greatest accumulation of arrivals at your sites. And so you could create a cumulative frequency plot or something like that after summing the first detection of each tag over time. And we won't have time to go through this today, but the code for this will be in the script that we provide. So on to example 2. This is a dual axis plot. A dual axis plot is really useful when you want to display two different variables on different scales. And we're using, again, that fish passage and spill data set queried from Dart. And you can see when you pull the data in from the Dart query, the data are in long format with two variables set in one or stored in one column, this data type column, with another column showing the values for those variables. And we'd actually like to transform this into a tidy data format so that the variables are each in their own column and the values are in rows. So there are many ways of doing this, but I'll show you one option using the pivot wider function from the tidier package. We specify the data frame name here, and then we just we set two arguments. Names from is the column that contains the names of the variables we want to widen by, and then we set values from to the name of the values column. And there we go. Now we have our data in a nice, tidy, compact format. This next argument here was just me cleaning up the column names a little bit. I'm using col names and then the name of the data frame to replace the previous header with these labels here. And then the last thing I want to do to this data set before plotting is to create a new date column. I want to change the format of the date. I don't really like this month day format here. So I am going to use the paste function again to concatenate just a year onto that month dash day. And we do that using this function with the separator dash. So again, functions very similar to concatenate in Excel. And now it's been converted into a date data type as well. So making a dual axis plot in ggplot is a bit of a hack in that ggplot requires you to plot both y-axes against the scale of the primary or the first y-axis. And so this means that you need to set a scaling factor for the variable on the second axis so it plots correctly. And we do this by first getting the min and the max bounding values for each y-axis. And we'll have adult counts on the first y-axis and spill on the second y-axis. And then we just use the functions min and max to find the min and max for each variable. And since there are NAs in the data, we have to use NA omit to remove the missing values before summarizing. And then we set this object scale, which contains the results of dividing the range of the second axis by the range of the first axis. And this results in this output right here, which shows us that our scaling factor is roughly 0.02, meaning the spill values on the second y-axis will be roughly 0.02 times the corresponding values on the first y-axis with the passage data. This will make more sense in a moment. All right, so for this example, we'll go through the ggplot step by step so you can see how the components build on each other. So we start by specifying our data set again within the ggplot function. And we also specify our variables. We have two this time. We have our x-axis equal to date, and then we have adult passage data on the primary y-axis. And then we're using a column geometry, geom_col, so the passage counts show up as filled bars. The color argument here controls the outline color of the bars, and then fill controls the fill color. And these are just hex codes that I provided corresponding to manually selected colors for each. And with that, we have the data for the first axis of our plot, which is adult passage. Now we add our second y variable, spill, as a line geometry. And we're doing something sneaky here. We're covertly dividing each spill value by the scaling factor, so it's put on the same scale as the adult passage counts. And we're again manually setting a color and a size for the line. And like before in our previous plot, we have scale x date, which defines a date axis, and then we have a continuous y axis which is indicated with scale y continuous, and we set the limits of this axis using the min first and the max first objects that we calculated earlier. And we also have our axis name here, the primary axis name in the quotes. And then here's the second part of this this trick that we do for a dual axis plot. we're using the ggplot second axis function here to build a second y-axis based on a transformation of the first axis. So now we need to multiply the first axis by the scale factor to get the values for the second axis. And the syntax for this is this tilde and then a dot, which is a placeholder or shorthand for data, and then an asterisk, meaning we're multiplying by that scale factor, 0.02. And then this last argument is just setting the name for that secondary y-axis. So now you can see we have two labeled y-axes in our ggplot. And now these last lines of code right down here are just adding a title, specifying a black and white theme, and specifying the text color, size, and a face for each axis label. And to make the plot easier to interpret, we just color the different y-axes to match their corresponding data. So that's why we have these two arguments here, axis title Y with an element text and a color specified, and then axis title Y right has a different color specified. And if the dual axis plot is too busy, you can also make as a multi-panel plot. I really like using the cow plot package from R, which lets you build plots into a customizable grid, and you can add panel labels like this A and B here. And R also makes it really easy to save plots as a specified file type and a size and a resolution, so you can make sure your figures are complying with publication standards. So if you're looking to have full control over your graphics, learning R and ggplot is really essential. And I'll use a fish pun here. It can feel like you're swimming upstream initially, but with practice you might get hooked, especially after you see the other features Jenny will talk about now.
Okay, so the last section that we're going to be talking about, I'm just going to expand visualizing data that Jen was going over with maps and some spatial data. So today I'm going to be doing a little introduction to maps and spatial data in R. I'm going to be talking about both static maps and also interactive maps using the leaflet package. Today I'm just going to be going over using vector data in R, so points, lines, and polygons, and I'm not going to be talking about raster data, but you can also easily handle raster data in R. We'll have some links to helpful resources that we send out later. The Terra package is most often used for rasters in R. Okay, so to even just create our spatial data in the first place, the SF library is very widely used for working with spatial data in R. And all you need to start out with is a simple data frame, and your data frame needs to have fields or columns for lat and long. So right here I'm importing a CSV that I downloaded from the PTAGIS website that has all of the PTAGIS sites and their locations and then some other information about each site. And this is what part of the data looks like. So we have a site name here, and then we have our lat and long fields coming in as decimal degrees, and that's how it looked when I downloaded it from the PTAGIS website. So if we want to transform that data frame into a spatial object, we basically use this function from the SF package that's called st_as_sf. And so now I'm creating, and I should mention SF stands for simple features. So now I'm taking that PTAGIS sites data frame and I'm creating this PTAGIS sites simple feature spatial object. And I'm telling the function using the argument chords that I want to create the spatial object using the columns lat long. And then we also have to assign a CRS or a coordinate reference system using an EPSG code. So that coordinate reference system is, just the datum that you want to use. And there are a lot of different EPSG codes. Each one specifies a different datum. And so I'm saying I want my CRS here to be the code 4326. And that's just indicating that I want it to be WGS84. And so if I look at the summary after I run this function of what comes back, R is now telling me that I've got a new simple feature collection, and I told it to return none of the rows. That's why it's saying 0 features. But I have a simple feature. I have a CRS of WGS84, and then it's listing all of the column names that are associated with those data. And if we take a quick look at the data, you can see that this function will automatically delete those lat-long fields that I started out with and replace them with this field called geometry. And that geometry is really what makes this a spatial object. So the geometry here is saying that we have point data, one coordinate point for each of those PTAGIS sites. And this is the coordinate for that point, and it's in the WGS 84 decimal degree format. Of course, you can transform the CRS of your spatial objects. Say, I don't want it in WGS 84, I like to work in UTMs. So we just have to use the function stTransform, and then you just simply assign it a new CRS here using a different EPSG code, and this EPSG code corresponds with NAD 83. This is for UTM Zone 10. So then when we summarize this new simple feature, we can see that we have a projected CRS of NAD 83 UTM Zone 10. And then when we look at the data again, we can see we have that same geometry column, and we still have it as a point, but now instead of those decimal degrees, we have the UTMs corresponding to easting and northing. Okay, we can also import shapefiles that you already have on your computer. So it's really easy to create simple things in R, but for a lot of the more complicated shapefiles, say they're already things you work with in ArcGIS, you can just import them into R, and it's usually a little easier to do them that way. So I have this cool stream network shapefile that I got from the state of Oregon in ArcGIS, and it's saved on my computer as a shapefile. So I just want to read that into my R session, and I'm using the function stRead. And then here's the name of my shapefile, large Oregon streams. And then R is automatically telling me that it's reading in that, that data using the Esri shapefile driver. It's giving me some information saying that it is a simple feature with over 75 rows of data and 38 fields. It's a multi-line string. And then it's telling me the CRS that it's automatically coming in as. So this is WGS 84 pseudo Mercator, which is the CRS that a lot of like web applications use. So it's a little different from the WGS I was specifying before. So I'm going to actually just transform it to be the same as the simple feature that I created that has all the PTAGIS sites. So that, you know, this is just like ArcGIS, you know, you have to have the same CRS or datum for all the information that you're working with if you want them to mesh together well in maps. If you don't have the same CRS, you're going to encounter some issues and things aren't going to work correctly. And then you can also export shapefiles that you create in R. So you just use this function here called stWrite, and then you just say, I want to export this simple feature PTAGIS sites SF that I created in R, and I want it saved as this shapefile here. So that's really useful too. Okay, so let's talk about building some simple static maps. So there's a couple options for base layers. So say I want to create a map of the state of Oregon and I want to show all of the PTAGIS sites within Oregon. So the first thing I could do is I could import a shapefile of an Oregon outline that I already have. So that's what I'm doing here. I showed in the previous slide. Just remember to check that CRS to make sure that it's the right one that you want. And then you can use base R, like Jen mentioned before, you can use the plot function. To kind of start looking at these really simply. So you can say, I want to plot, and then the Oregon shapefile, and then you use this function that is from the SF package called stGeometry. So that'll pull up the Oregon shapefile. And then the plot function just adds new layers on top of each other. So then you do this next line down here, and then you say, I also want to plot my PTAGIS sites and add it to my Oregon shapefile that I already have. And then you come up with this, this map right here. You can also download polygons for base layers from available R packages. There's a lot of packages that do this. I'm showing R Natural Earth and R Natural Earth Hires here. So they have polygons of all different countries. And you can look up all of the different ones they have are available online. So I'm saying, hey, I want to use the any states function to download all the polygons in the United States. And please return them as this class of simple features. And then so that loads into my R session and I say, well, now I just want to subset the state of Oregon. So I use base R to subset just Oregon from that simple features. I transform it to the correct CRS. And then I'm plotting it just like I did in the previous slide, and you get the exact same map. But as you noticed in my previous slides, the PTAGIS sites, I didn't just have the Oregon PTAGIS sites, I had some of the other ones too that were up in Washington. So we can do some simple spatial operations. The SF package has a lot of simple ones, but there's lots of different packages in R to do spatial operations. You can do things like easily, you can do clips, buffers, measures, and joins, but there's a lot more advanced spatial analysis you can do in R as well. I'm just not going to go over that today. But you can use, if you want to clip one simple feature to another, so I just want to clip all of the PTAGIS sites within the state of Oregon, I can use this ST intersection function, and it will return a simple feature of PTAGIS sites Oregon that are just within that Oregon boundary layer. And then again, I'm plotting them, and now you can see I just have the nice sites that are in that Oregon base layer. You can make them look a little bit prettier by adding some colors. So here I'm adding in that stream layer that I got from the state of Oregon. So I'm overlaying that, and I'm making this stream layer blue by using this hex code color. And then I'm filling in my PTAGIS sites that are in Oregon to make them a little more visible by changing the symbol using this PCH argument. And 19 just specifies that I want it as a solid circle, and then changing the color there as well. So those are simple maps using base R and only a couple packages. Now you can also use ggplot for some nice stylized maps, so especially if you're going to do like a publication or a fancy presentation. And there's a lot of different ways to do this. T-maps or thematic maps is a really popular package that you can do a lot with, but I'm going to talk about creating some of these maps using ggplot because Jen did such a nice job of describing the ggplot package earlier. So to create maps in ggplot, it's really simple to creating other graphs and graphics. You're saying that you want a ggplot, and here for the simple features, you're just saying I want the geom SF, so geom simple feature, and you're just adding layer upon layer. So I'm adding my Oregon layer, I'm adding my stream layer, and I'm adding my Oregon PTAGIS sites layer. And so you just get this like really simple kind of, basic map here to start out with. And then we can add all of those fancy things that Jen went over earlier to make colors and to add titles and to change the aesthetics of your ggplot. I'm not going to go through all of these lines of code because we do not have time for that. But one thing that I also did here is I said, hey, I want to have a different color palette for the PTAGIS sites in Oregon that are active versus inactive. So I changed the active sites to a red color and the inactive sites to an orange color. And so now you're displaying that on this map as well. And then this gets you a little bit closer to something that's a little nicer and shareable for other people when you're really wanting to display data. Okay, you can also add imagery to ggplot maps. So you can use some satellite or other imagery. Again, there's a lot of popular packages that do this. I'm going to show the library base maps. Basically, there's a function in base maps that is called get map types, and you can use this to generate a whole list of all the different base maps that they have available. I'm going to use one from Esri called world imagery, so it's just simple imagery. And so I'm setting my default map service to that Esri world imagery here using the set defaults function. And then like I mentioned before, a lot of these web mapping applications use this pseudo Mercator CRS. So I am just going to transform my Oregon shapefile data and my PTAGIS sites data to that CRS because I found it's a lot easier to do it on my end than try to change these base maps. I think it's possible, but I don't even want to mess around with it. This is much easier. So I've changed that CRS to match with the world imagery that I'm bringing in. And then I'm saying, hey, I have this world imagery, but I just want it for this little area of Oregon that I'm interested in mapping. So I'm going to set an extent using a bounding box with this stbbox function. And I'm saying I want my bounding box to match my Oregon simple feature layer that I already have. And then I'm just doing my due diligence and I'm just making sure everything is matching correctly, and I'm transforming my CRS to match everything else for that extent. So like I said, that EPSG, 3857 is widely used for online mapping platforms. It's easiest to transform your data to match those. Some background maps require API keys, such as the Google Maps. And I'm not going to get into that. It's basically, API keys are basically a way to interact with websites and download data for them. But many, like the Esri base maps, are available for free. Okay, so here I'm adding this base map that I downloaded using the base maps package into ggplot. And all you do here is you add this simple function called basemap_gglayer, layer, and then I'm saying I want to use that aerial imagery of the extent that I specified before. And then I'm adding, you know, my other things that we've already gone over, and the result is this nice map that has the aerial imagery with my Oregon PTAGIS sites on here. And then the last thing I'm going to go over quickly are interactive maps using the Leaflet package. So Leaflet is basically just a really nice package that lets you use interactive maps where you can pan and zoom and click on things. So right now, and Leaflet is very similar to ggplot, where you're just kind of adding things onto each other, except instead of the plus signs, Leaflet uses this piping operation that Jen was talking about before that is associated with the dplyr and tidyr packages. So right now I just have a blank map. I'm just calling Leaflet and I'm saying I want a tile, which is kind of the Leaflet lingo. So if you want some nice imagery, you can add a certain provider tile. So I'm saying I want the Esri World Imagery provider tile in my Leaflet map. And if you go online to the Leaflet documentation, they have all of the different imagery that you can access through Leaflet. And then I'm saying I want to set my view for my Leaflet map to a specific coordinate. So I'm saying I want it to center on this Latin long, and I want it at this zoom level. And so this Latin long is somewhere here in Oregon along the coast. Now, you don't have to do this. Once you start adding your simple features data, Leaflet will automatically zoom in to basically the bounding box of whatever data that you add. But if you really want to customize it, you can set the view here. And then finally, you can do some things like you can add your circle markers, which is basically the PTAGIS sites. You can do things like pop-ups that have the site name. So if I click on these PTAGIS sites, it'll say the name of the site. You can color them differently. So I've colored these to correspond to what type of site it is. So is it a fishway, a hatchery return, etc. And you can zoom in on these nicely and see exactly where they are. There's some really good definition for these Leaflet maps. And then I'm also adding a legend with this add legend function here. And then finally, I'm just going to give one more option for writing image files. Jen already did one earlier, but specifically with the ggplot2 package, you can use this function ggsave. And it'll take the last ggplot that you've created, and you can save it as any kind of, as multiple different file types. So here, this example, I'm saying, hey, I have this simple ggplot of this like really minimal map that I created earlier. I want to save it as a PDF. I want it to be this width and this height and this DPI. So again, like Jen said, these are really great ways to create publication type images, and you can control exactly how you want them to look. Okay, thanks everyone. So I know we covered a lot of ground today, and we weren't really able to go into the details on every small thing, but we will be sending out our contact information as well as this presentation, some code to do everything that we did in this presentation, and a ton of links to additional resources after this presentation is finished. So please feel free to get in touch with either Jen or I about the material that we covered today. And even better, if anyone wants to talk about herps, we would love to do that too. So thank you, everyone.
Awesome. Wow. Thank you so much, Jen and Jen. This is the third Jen today, in case you were confused. I had nothing to do with any of that. It was so amazing. We do have a few minutes for questions. We're going to shift gears here pretty quick. Any questions, you can raise your hand. You can drop your comment, a question in writing in the chat. We'll also, if you're still like digesting all of that, we'll have some time after our next 3 presentations where you can ask questions of any of the speakers today. And as Jen mentioned, we will share a whole bunch of resources after this, so you can contact Jen and Jen, or and also get the code. And there's a lot there. All right. Not seeing any questions. Anybody? Going once, going twice? I should have my share my slide briefly just to remind everyone where we are in today's presentation. Any questions? All right. Well, thank you, Jenny and Jen, and stick around. I'm sure someone has some questions at the end here. So the next part of today's episode of the webinar series is Monica Diaz presenting on the Klamath Basin Fisheries Collaborative Database. So this is where we're shifting gears, and we're gonna have 3 shorter presentations where folks are sharing work from outside the Columbia to learn how we might make some friends that we didn't know we needed. So welcome, Monica. I'll let you take it away. Thanks.
Okay, I'm assuming everybody can see my screen.
I can see it, and you're coming through loud and clear.
Okay, so I am Monica, and I'm with Pacific States Marine Fisheries Commission, and I'm part of a team that supports the Klamath Basin Fisheries Collaborative, or KBFC, or the collaborative. And we support the leadership group and work alongside USGS for this project. So there have been years of collaborative efforts within this basin across 30 plus entities collaborating on like pit tag projects, and there was no standard way of collecting all of that data. So I can imagine everybody here can probably imagine the frustration and how slow it was to share data with all of the cleaning that had to be done while you're trying to get reports out and collaborate on projects. So these partners came together to create the Klamath Basin Fisheries Collaborative to standardize pit tag data and track fish and monitor fisheries within the Klamath Basin, and to support endangered species and develop crucial insights into the Klamath Basin's river ecosystem with pre and post dam removal. So the main goal of the collaborative was to standardize pit tag data and its associated metadata to its members. With standardized data going into the database, new projects and collaborations can actually happen faster and get reports out faster, be used for research and management decisions. And it also just creates a stronger collaborative network with its current members and any future members. So its main focus is on fostering information and sharing within the within its members and any other interested parties. The KBFC has a leadership team, and they are the primary decision-making body that guides the collaborative. They meet 4 times a year. They discuss research findings, priorities, and focus on maintaining database integrity. And one of their main goals is to also foster information sharing and communication amongst its members. We also have the annual meeting, which we just had earlier in May, and that's a way for its members and interested parties to come together once a year, in person and virtual, to share their research, their projects, and foster discussions to create coordinated projects within the basin. And then we also have working groups that form, and their goal is to focus on collaborative research questions and to also find data gaps within the database. And then we have the database, which is designed to support the pit tag data sharing and coordination. Right now, it is restricted to members, and membership is approved by the leadership team and agreeing upon the data sharing agreement. So, quick review of what we have created. The user interface, or the database system, has went live the end of last year. So on the left-hand side is an example of what the general public website looks like. We post the data exchange standards and controlled vocabulary on there, the sharing agreement, the API data exchange, and that is open to the general public. So if interested parties can come in here and look and understand what data is going into the database and what we're looking for with the data sharing agreement. On the right-hand side is an example of what the user interface looks like once you log into our data system. We have these quick data visualizations, which is shown on the bottom right. And then on the top is what it looks like when you're actually looking at PTAG data. So a user has basic data management functions in here. So uploading, editing, and exporting data. So now that it's, so we also have the tag history search, which is similar to PTAGIS. And I forgot to mention, KBFC was actually created to be very similar to PTAGIS because they wanted to create this cross-basin reporting system. So the data being housed in KBFC is going to be looking very similar to what PTAGIS looks like. And the tag history search is similar to what PTAGIS has. And then we will also have a general public search on the main website. And so a main example of using that feature is because of avian predation, we have a lot of pit tags that end up in the Columbia Basin from the Klamath Basin. And so these unknown tags can be searched between the two systems, and the data will look very similar to when you're trying to find out the information for that tag. And then with the database live, the data can now be used for individual agency needs as well as broader agency goals. And this is a quick example. I think most of us here are pretty familiar with data exchange standards and data sharing agreements and controlled vocabulary. So we combined the controlled vocabulary and the data exchange standard for ease of use. The leadership team worked with all of its members to come up with this document. And this is a quick way for users to understand how the field names are being described, as well as the format of the data that's going into the database. And the data sharing agreement is there to inform the members of their roles and responsibilities when they contribute and share data. So all three of these documents are just supporting and helping with data transparency. So there's no confusion about what the data is, how it's being downloaded, how it's being used, and it just makes it understandable between all parties. So some quick statistics about our database. We're pretty new. We have about 22 active users right now. We, with going live last fall, we worked with a lot of entities to crosswalk their data to get it into the database. And that with historic data, we ranged back to 2006, and right now we're current as 2024, but we do have projects that are actively collecting data right now in the field. And so soon that data will be able to get uploaded into the system. So we are collecting data beyond salmonid species. We have a huge sucker monitoring program with USGS and the tribes, who are also collecting pit tag data for those species. And we also developed some ESRI Survey 123 forms. A colleague at USGS, Rachel, spent a lot of time collaborating with a lot of entities that are going out into the field and making sure that survey worked and made sense while they were in the field, and as well as making sure that we are collecting data outside of the database so that it can be used in that form and not create a situation where they're using like 5 different forms to collect data. And that took a while. That took a lot of travel out to the entities and doing some mock field data collection to make sure that that worked. And I think she did an amazing job. So our current progress is the data went live, or the database went live last year, in like November. So our team worked really close with entities on converting their old data to the current KBFC data exchange specifications. We also have these data uploading templates that entities can use, and we work with them to be self-sufficient so that they can start crosswalking their own data to get it into the system, and everybody can work independently, and we're there for support if they have questions or if something's not working. Here's an example of the Esri survey form that was created for field crew, and that data is being standardized at a field site, and those forms, the data being collected in those forms can be easily integrated into the KBFC system, so they don't have to download it, clean it, and then upload it. So we're trying to make it really easy for entities to get data in to the system. And then part of a data modernization grant, which those Esri survey forms were part of, we also are creating internal databases for a couple entities where as they're collecting pit tag data, either with paper sheets or other Survey 123 forms or this KBFC Survey 123 form, they can house their standardized pit tag data in-house, and then those internal databases will then feed directly into the KBFC data system. So we're really trying to make it easy for entities to standardize their data, share it quickly, make it easily accessible amongst partners and for reporting, and also capturing data in the field. And so that was my very quick and brief overview of the Klamath Basin Fisheries Collaborative. And if you guys want any more information, we have our website, which is the QR code or the link below on the slide, or you can always reach out to me.
Excellent. Thank you, Monica. That is awesome. It's cool to see a brand new system being so thoughtfully put together, but yet building on what we learned through decades with PTAGIS. Very cool.
Yeah.
All right, it's on its way. Yep, looks great.
And thanks everyone, glad to be here. So I'm gonna just share a really brief overview with everyone on our Green River pit tagging program. So before I jump in, just to give you guys some background on how we got to this program. If you're not familiar with the Green River, the Lower Green in particular, this is a highly modified urban environment. We're talking 28 miles of levees and revetments for 22 miles of river. So you can guess what that probably looks like. From a lot of the past research that has built up to this point, we know that the fry migrants that we have leaving the river are just not surviving to adulthood. So you can see that in this figure here. This is adult Chinook otolith analysis done by WDFW. And despite having roughly 50% of all of our out migrants leaving as fry, less than 1% of those actually return to adulthood. So we know that really the par production is what is driving our adult returns. And from some additional research, we know that par production in our system is density dependent. So, we are only capable of producing a finite amount of par. And if we want to make meaningful gains in salmon recovery, we need to increase the amount of habitat available that can grow those fry into par migrants. So one of the big questions the last few decades has really been, is this highly altered lower green environment providing that habitat that can grow those fry migrants into par and thus contribute to adult returns? And on top of that, can habitat restoration here increase that par production? And that's a big question. In an urban environment, restoration is incredibly expensive. Not just the property, but you also have highly confined areas with a lot of flood control infrastructure too. So we need to make sure that if we're going to be investing in these projects, they better work. So why pit tags? The last several decades, there has been a ton of great research, but it has always left us with some very big data gaps. So screw trapping has been attempted here, but it's a very slow moving river without a defined thalweg. So trapping is really inefficient. We've done a lot of work electrofishing and snorkeling, which is great for habitat use and comparing habitat use over time and species, but it's really just providing us a snapshot. In order to answer this question of, providing, par habitat and places for these fry to grow, we need to understand residence time. And on top of that, there's other lingering questions like survival, which up until this point have just been completely unknown. So, pit tagging is obviously not new, and these ideas have been thrown around for a long time. But, as a lot of traditional pit tag antennas are really difficult to operate in main stem rivers. So, picture rectangular antennas. They're very susceptible to damage in high flows, vandalism, but also main stem river like this, where your water surface elevation might change 10 feet in the rearing period. Your efficiency is going to be highly variable there. Also with the standard 12 millimeter tags that have really been the go-to for Chinook monitoring, forever. Those are really too big to help us answer the questions about those smaller fish that we know are not surviving to adulthood, those fish less than about 60 millimeters. So with some relatively new technology, we decided to go with this pit tag route. And we have been using the West Fork environmental fin array barges as well as 9 millimeter pit tags. So if you're not familiar, this photo here shows one of these fin array barges. Floating platform are custom made 24 by 24 feet. So you basically have vertical antennas that act as hydrofoils down in the water. The whole entire unit is floating on the surface. So, it's operating in that upper water column regardless of flow. Our anchoring system is overhead, so we don't have to worry about, the anchoring system catching debris. And really, it's set so that it can shed debris well. And we've had this thing operating, from base flow all the way through big floods with no issues. So, in terms of salmon recovery, the reason why we're doing this is, as I mentioned at the beginning, we're trying to really guide our investments in salmon recovery. It's very expensive to do these projects, and there's just never enough money to do the projects we want. So when we get money, we want to spend it as effectively as we can. So with this pit tag data, it's helping us to, one, find the best locations for habitat restoration that are going to be most useful, help us create effective habitats, ones that we know will be used and will be used often, as well as identifying flow ranges to provide habitat. We have these highly confined systems where we're lacking a lot of floodplain habitat. So, these pit tags are helping us identify flow ranges in which, refuge and ring habitat might be most limited. In addition to that, this is helping to identify other limiting factors that maybe we didn't know about or understand previously. So a little bit of timeline for you. 2021 is really when we got the ball rolling on this. And it was our pilot year to test the West Fork environmental barge, as well as the 9 millimeter tags. And this was done in Lower Green. We also sampled a couple of tributaries as well. And this program has grown since then. 2023, we incorporated the use of an additional barge. So with the two barges, that's big because that enables us to use these two detection points to run mark recapture models, which in turn help us calculate survival. We've also expanded to some recently completed restoration projects. And 2024, we expanded even further to address the entire river system, basically. So we're able to look at the Lower Green, which is the heavily impacted area, as well as the Middle River, which is basically from Auburn everything up to Howard Hanson Dam, which is usually considered our better habitat. Moving on, this year we will be installing an adult antenna to track our pit tag fish coming back. And next year we will be doing the two barges again, as well as incorporating mobile tracking into our program. So actually rigging up a raft with a floating antenna where we can actually go out and hunt for fish. So I'm just going to touch briefly on some of the key things that we have learned. Obviously, we could talk for hours about this, but at a high level, our 2021 study, that was a big turning point. So we confirmed that, yes, in fact, Chinook are using the heavily altered lower green for long-term rearing. So, we're talking, upwards of months in this system. So we know that this area is contributing to par production and thus, contributing to adult returns. Um, that's important. Again, there has been a lot of thought that it's possible that fish are just passing through this area. To us, it just does not look like fish habitat. But for the fish, it's working, at least in some regards. The study also found long-term rearing occurring in several non-natal tributaries. So documenting the importance of some of these types of habitats, as well as the role that they can play in salmon recovery. Our overall test found that the barge was effective, so we averaged a 9.2% detection efficiency. So, for main stem, mid-river arrays, this was great. This was better than what we expected. And, without, dams and the other infrastructure for, pit tagging equipment, it's difficult for us to get these detections throughout the rearing period at various environmental conditions during a study. So this was a success for our program. And then the 9mm tags as well. So, you get less detection range than the 12mm tags, but, we got that 9.2% efficiency with it, which is great open water efficiency with these smaller tags. But we also were able to tag fish down into the 40s with no apparent risk to health. So overall, I think out of the 4,000 fish we tagged, we had 6 of them die over a 24-hour holding period. So we're really happy with those results. Building on that in 2023, we expanded our release locations to look at subsections within the lower group itself. So one of the things that we found from that initial study is that our estimated survival rates were really poor in the 20%-ish range. So we wanted to look and see were there differences within this study area. So we divided that into 3 sub-breaches, and what we found is that one of these sub-breaches did have significantly less residence time than the others. So this is useful in helping us identify areas where habitat might be the most limited and where we should focus our restoration efforts. We also found in the study that these tag par were not moving out of the system at high flows as we expected. Higher flows actually stopped their outmigration and then resumed again as flows were decreasing. So our detections during the actual par outmigration were highly associated with decreases in flow rather than high flow or increases in flow. During 2023, we also looked at 2 new habitat restoration projects, both a large backwater and a side channel. And really the big takeaway here is that we had tagged Chinook in these projects basically as long as there was water. The second that they filled up with water, within a day, we had tagged fish moving in, and they stayed during the entire study. So they stayed there up until the last minute that water was draining out of them as flows dropped in the late spring. So this was huge for us. This is proof of concept that our projects are working, but that we need to be providing habitat at a full range of flows so fish can use them. We also, with multiple antennas, found fish that were actively rearing in these projects, they moved like very little, So we saw the majority of these fish stay within maybe 100 feet through the whole rearing period. And we didn't see them move again until, they were out migrating from the river. So what's next? We collected our 2024 data. As I said, we had the 2 barges, we had upper river and lower river. So we are currently processing that data with a CJS model, evaluating survival rates between the 2 groups and multiple groups over time. So that will be coming up soon. This fall, again, we'll be installing the adult array, which is really exciting. It's great to see those fish coming back, and it really, pieces the whole thing together to see which ones actually return, which is the overall goal of salmon recovery anyways. And then beginning next year, we will be doing, as I said, the mobile tracking. And the mobile tracking is really going in at a finer scale. So that's helping to look at, exact habitat use and rearing locations. But then in combination with the barges, we're able to see how the use of those certain habitats and locations correlates with the probability of detection as they outmigrate. So what rearing habits are actually improving their odds of surviving as they leave. So with that, yeah, thank you guys. I know it's really high level. There's a lot of different things going on here, but you guys are more than welcome to reach out, email me, call me at any time if you have questions or you're interested in any of this data. Thank you.
Awesome. Thank you, Chris. Wow, what a great set of presentations today. Wide range of scale and different applications. Our last speaker there was Chris Gregersen from King County. I'm going to flash the overview slide of all the talks today. I wish we could give a very loud round of applause for Chris and Bram and Monica and Jenny and Jen, because it's been amazing, as well as all the presentations through the previous 4 weeks. Wish Meg Detloff could be here so we could thank her in person for her efforts to get this going. But I'm really grateful everyone was able to see it through till the end. So we're going to open it up for general questions. I do want to show one more slide because I know I'll start to lose people. And Amy's going to drop a link in the chat. I want to thank everyone, but I also want to ask you for one more thing to help us shape the future of what PNAP might do to help you, our community of practice, with respect to this topic and information sharing. When we started the 5-week webinar series, we had the idea that we might want to do maybe in-person, longer workshop. And if you've been through all 5 sessions, you know they're a little bit different, some with a longer presentation today like we had from our USGS colleagues, and then some shorter ones. I think in particular today, I'm sure we could have spent a lot more time learning about the new system, or the new to me systems that Bram shared. So we're dropping a link to a survey. Tell us your thoughts, and know that we're going to come back in the fall, and we'll probably ask you again before then. But if you help us now with some insights to help us plan what we can do to help you down the road. Also, some news for you all is that PNAP will be hosted soon by Pacific States Marine Fishery Commission instead of USGS. So you'll hear from us over the summer from our new email address, pnap@pfmfc.org. So don't be surprised when you see that. You go ahead and add that to your contacts so we don't end up in your spam. That'd be great. And we'll see you in the fall when we have our, we're back up and fully staffed, and we start resuming the fish monitoring work group meetings. So with that, I do want to go backwards to this slide because we do have about 15 minutes or so. If people have questions for any of the speakers today, if you guys want to turn your cameras on, you can drop your questions in the chat, or you could turn your camera on and ask your question yourself. Or if any of the speakers have other comments they want to share, I did see some links in the chat dropped. We'll make sure to grab those and share them when we send out the meeting summary, which will probably be Tuesday of next week. We'll share a link to the recording, as well as any links we have from our speakers today. Russell.
Jen, just as one of the helping the planning committee for this, I want to thank all the talks speakers for contributing. And as you said, the important part of the survey I just wanted to highlight, we have been collecting and grabbing the tools and the resources, and one of the intents for PNAP at least was to help share tools and products from these types of talks, and from pit tags, for managing pit tags, doing analysis, or managing GitHub or R codes. So I think that's a question of, when you do the survey, keep in mind that as a forum, PNAP can help us share our tools better across the region. So I want to thank everybody for the shared codes, the shared learning that started with the 5 presentations. So thank you.
Thanks, Russ. Good reminder. Yeah. Anyone else have any comments, questions, news to share? The office hours idea was meant to be, could be any question or discussion topic related. We had a lot today. It was a lot of information. So this is no like glide path to the end. No, the last session is equally jam-packed as the first, second, third, and fourth. All right. Well, I think maybe it is lunchtime, which does happen.
Jen, should we repeat the question that Ben asked or was asked? What was your biggest challenge? Or what is your biggest challenge or
right. He had
hack
something about
to use that?
workaround. Yeah,
Yeah.
exactly.
What's your favorite hack?
Hack. PTAG data analysis management.
Or all the humans in the Klamath Basin management?
Or the Salish Sea, multiple countries, and yeah, a lot. What have you guys got? Any insights to share? Mari, I see. It looks like you turn your camera on, but it's black.
Oh, yeah.
Maybe you have a little thing over it or something. There you go. Hi, Jen.
Hi, if I could just go real quick. I would say, as far as hacks go, I think one of the big ones that Jenny had brought up is pulling in your data with your PTAG codes and already from the start setting the column class as a character as opposed to just allowing R to pull it in and then sort of decide on what data type it is based on the format of the field. We discovered, yeah, like Jenny was saying, with our PIT tags that are in numeric format and 16-digit long codes, that oftentimes we were having issues with R converting those. So I think you learn really quick that you need to handle those certain PIT tag data types carefully. And then I don't know, other hacks, it's sort of tough to say. It'd be interesting to see what other folks think too.
You all definitely had a presentation chock full of hacks or tools. It was a lot. Good job.
It's a lot.
Right. You just really have to think through just the structure of your data, and for every question that you have about it, just think through like the steps for how you're going to, transform your data from point A to point B. And I think it takes just some time learning.
Thanks,
Thanks
Jen.
for sharing all of that. Chris, did the bear make it into the orphan tag database?
That bear was probably the nicest piece of garbage that we had wash up on our barges. I will say, no, Bram and his team, their database is incredibly helpful. So we've actually had a couple tagged fish show up on our antennas that Bram was able to find the metadata and the owners for those tags. So helping us piece that together.
Awesome.
And
Do
I will
those
say I don't
overlap
see
with the herps? Do Jenny and Jen find their tags in the orphan tag?
maybe you might not travel. I think you're muted.
No. Yeah.
No, I don't think so.
I will say I don't see Ralph Lampman online at the moment. He's with the Yakima Nation, Bram. We need to introduce you later because he was the one very eager to learn about where he might find pit tag detection data for lamprey, because we know they're not as stray is not the right word with lamprey, right? They have a different life history strategy than salmon, so they might go anywhere they wish in the Pacific. So yeah, we'll make sure you connect. He asked repeatedly, but I don't see him online right now. So his loss, but we'll make it happen.
Sounds good. Thanks. Yeah, and as far as hacks go, I don't know if I don't know if you would really classify it as a hack, but to follow up on what Jen said about the tag strings being treated as characters and not as a decimal data type, because Excel and R might decide like to be helpful and just trim that down for you, but you end up losing the valuable information. I think in general, you know, minimizing human involvement, like anytime a human can touch the data, it opens up the opportunity for human error. And so the way that we've built our system using ODK so the field crew member collects the data and it immediately goes into the database. We just try to minimize the amount of opportunities for human error and let the machine do the work as much as possible to control the data quality. So I think just a general rule of thumb, maybe it's not really a hack, but you know, anywhere where a human can touch the data is a potentially an area where errors can slip in.
A good approach, no doubt, saving time and effort later for sure. Good question, Mari. Thank you.
I stole it.
Was a good prompt from Ben. I think that was week 2, maybe. It was early. It was a while ago. We've been reusing that. It's nice. Any other questions? Any other remarks? All right. Well, you'll see an email. And these emails are going out cumulatively each week. It's a little bit longer list. So we'll capture the details from this set of presentations today, but we'll also share the link to the survey, and you might get a reminder maybe one more time, but then we're going to be a little quiet for a while, and you'll hear from us again later this summer from pnap@psmfc.org. Thank you for the speakers today. It was excellent. So much great information. Really exciting. Have a great rest of your day. See you soon.
Thanks, everybody.
Thank you all. Thanks for organizing.